Welcome to the MIT Enterprise Forum, the future of space, the challenges of getting to Mars and back. Good evening. My name is Richard Deininger. I led the planning team at the MIT Enterprise Forum Northwest to develop the program tonight. In case you don't know, the MIT Enterprise Forum is a global organization of dedicated professionals with 25 local chapters affiliated with MIT through the MIT Technology Review magazine. We inform, connect, coach technology entrepreneurs, enabling them to rapidly transform ideas into world-changing companies. We are a volunteer-run organization who seek to be inspired and educated through technology leadership. Please join us for some related programs later this year, all on the theme of the future of artificial intelligence, the human body, which is next in January, and the future of fun. This program and those to follow really would not have been possible without dedicated volunteers. Those helping us with the current program are Marcy Rugland, Shirley Lundy, Vicki Owens, Chad Evans, Adam Schuster, Nat Seymour, Andy Silver, Paul Meehan, Nick Hine. The programs are made possible by our sponsors, the season sponsors at the premier level, T-Mobile, lead sponsors, the Artifact Group and Summit Law Group. In-kind sponsors, Freelock Computing, MIT Club of Puget Sound Video, Pinchot University, Net Reflector, MIT Alumni Club of Puget Sound. Now I had that in there twice, didn't I? All right. Well, I went to MIT, what can I say? And we'd also like to thank our program captains tonight, which are supporting the chapter by purchasing a block of tickets. They are Dorsey and Whitney LLP, Highline Schools, and I can see we have a lot of students here, that's great. The Mars Society, the National Space Society, local chapters of both of those organizations, the Space Entrepreneurs Meetup, and the Seattle Futurist Society. Please see one of us if you are interested at all in becoming a program captain yourself for a future program. Our moderator tonight is Alan Boyle, who will also provide an additional introduction to the subject. Alan Boyle, as many of you know, is the aerospace and science editor at GeekWire, the Seattle-based online news operation that this audience probably knows fairly well on all technologies and topics that warm a geek's heart. Before joining GeekWire, Alan was science editor at NBC News Digital, previously known as MSNBC.com, from '96 to 2015. He's covered Mars exploration, commercial space ventures, and other way out topics since the Mars Pathfinder mission of 1997. He's also won many prestigious awards, the most prestigious awards in his field. Alan is the president of the Council for the Advancement of Science Writing, the author of The Case for Pluto, How Little Planet Made a Big Difference, and a contributor to a field guide for science writers. Let's welcome Alan.
Thank you, Richard, and thanks to the MIT Enterprise Forum for sponsoring this event. In case you don't know, the title is The Future of Space, Challenges in Getting to Mars and Back. And so let's, there he is, Mark Watney. How many people have seen the movie The Martian? Okay, good. If you're a space fan, you're probably wondering, why can't we do that now? Mark Watney found himself marooned in the wilderness of the Red Planet, kind of looking over the scene and wondering where he was going to go, how he was going to go to find safety, to find survival, to find that place where he could get back into the swing of exploration. And we're doing the same thing here tonight, and we're doing the same thing with our space program, is that we're looking at this big expanse out there and trying to figure out how are we going to get from here to there. And so my role tonight is like the director of The Martian, Ridley Scott's role, to set the scene and let the people who really know what they're talking about talk about it. But in terms of setting the scene, I wanted to give a little bit of information about why we haven't gotten there yet. And it really comes down to the issue that has been in the space effort since the 60s, is that it's really a balance of political will and public enthusiasm versus the cost and the risk. Now, during the Cold War, we had this race to the moon with the Soviets, and it really was not a scientific race. It was an extension of the Cold War, that this was an idea where American technology could prove that it was better than the Soviets. And it kind of worked. It was pretty expensive, but it kind of worked, and it had an impact on how the world viewed America as opposed to the Soviet way of life. So since then, we've had other purposes for the space effort, that it's not so much a case of proving that the American way is the right way, although if you watch the Curiosity mission and the people flying the American flags when the Mars Curiosity rover landed on the red planet, there's a little bit of flag waving to this as well. Now, with the Curiosity mission, just to give you a little context on the cost, that was $2.5 billion for that mission. And that's a lot of money. But if you're talking about sending Mark Watney to Mars, it's going to be a lot more money. Right now, NASA's budget is about $18 billion per year, and $8.5 billion of that goes to human exploration and operations. That's the sort of effort that puts people into space and builds the stuff that's going to put people into space in the future. So $8.5 billion a year. How much is that going to get you? Right now, we're spending that on keeping the International Space Station in operation. Just today, commercial Cygnus cargo craft delivered more than 7,000 pounds of goodies to the International Space Station. There are 6 astronauts up there, Russians, Japanese, a couple of Americans. They've been up there since 2000, and we want to keep the space station going until at least 2024 and maybe 2028. So for the next few years, the International Space Station is going to be where it's at in terms of proving the sorts of things we need to prove to go further, to go to an asteroid, to go to Mars. The current space policy calls for going to an asteroid and bringing it back into a special kind of orbit around the moon somewhere around 2025, and then sending astronauts out to study it, maybe take some pieces back and practice the sorts of things that they want to do on a mission to Mars. And so that is kind of the approximate goal. That's kind of the next step beyond Earth orbit for what we're doing. And some people in Congress have been saying, I don't know if that's really what we want to be doing. How about we go back to the moon? Or how about we spend that money and just go directly to Mars? And so you don't hear about that political discussion too much, because you're probably hearing about other things like, what are we going to do about Syrian immigrants, or what are we going to do about Muslims in this country? Space is not a really high priority in the political debate. It kind of goes on in the background, but it is a very big multi-billion-dollar venture that commercial companies like Aerojet Rocketdyne you're going to hear from, and Planetary Resources you're going to hear from, Blue Origin, a local company, Boeing, another company with a big local presence. They're all involved in this space effort. So it's kind of important stuff. But to get to Mars, that's going to take a lot of money. The estimate is that if you spent everything over the next 20 years or so that we're spending right now on human spaceflight, $8.5 billion a year, you might be able to make it. You might be able to send astronauts to the moons of Mars. A particular moon that a lot of people talk about is Phobos, and you might be able to do that by 2033. The total bill is somewhere in the neighborhood of $200 billion if you add up all that money over the next 20 years. And in the past, people have talked about even bigger figures, like $400 billion. There was one figure that came out there. So the issue is, how much do we want to go to Mars? How much do we want to spend? How long is it going to take to do that? NASA is saying the 2030s. That's when we're going to take the journey to Mars. And this is the plan for NASA getting to Mars. So it starts out with the International Space Station. They're building a big launch vehicle called the Space Launch System. They're building a spacecraft called Orion. There's already been one flight test of Orion, and they're going to have another one around 2017, 2018. They're going to start putting people on Orion somewhere in the 2023 time frame. And then they're going to work on technologies. One is called solar electric propulsion. That's what Roger is going to talk about. They're going to be trying to build in-space habitats, a transfer spacecraft. In the meantime, they're going to have robotic missions going to Mars and trying to learn more about it, maybe bring some of Mars back for study. And so it's a long haul. That's the way NASA sees it. Other people think they can do it quicker. You may have heard about a guy named Elon Musk. He's a billionaire who founded SpaceX, is launching rockets to orbit, has had a setback or two lately, but that's what he wants to do. He wants to put people on Mars. He wants to make humanity a multi-planet species. He has said that he wants to die on Mars, but not necessarily on the way down. So that's what it's all about for him. And his plan calls for sending 80,000 colonists to Mars, and each one pays $500,000 for a flight. They're big believers. There are some people who would be willing now to go on a one-way trip to Mars. So if you multiply 80,000 times $500,000, you get $40 billion. And Elon thinks that he would be able to do this for $40 billion, which is a fifth or less of what NASA is thinking. And then, so here's, this just kind of recaps what I've been talking about, that there's a movement from being reliant on Earth resources to going to the area around the moon, something they call cislunar space. If you hear cislunar space, that just means between the Earth and the moon, and you can sound like a real space geek if you throw cislunar in there every once in a while. And then when you're Mars ready, you've got the rockets, you've got the hardware in order to do that. But Elon Musk thinks that he can do it quicker with a modified version of the spacecraft that's flying up to the International Space Station right now, the SpaceX Dragon. So watch for that. The private sector is in this game as well as NASA. And the last player in this I'll mention is Mars One. Now they're saying they could send 4 people to Mars for $6 billion, and then every 4 after that would be $4 billion. Now you really get out to the bleeding edge, you get to the fringe with some of these people. A lot of people aren't sure that Mars One will be able to do everything, and there's a lot of smoke and mirrors in the space business. And so you kids who are going to be voters, you have to watch for that. You have to really assess who can really do the job. What do you want as your priorities in our space effort? This is the next frontier. This is the frontier that is going to attract the best and the brightest to get involved in math and engineering and science. And so we want to do it right, and we don't want to believe everybody who comes along and says, hey, I can put people into space and do all this and be like Mark Watney and be like all the folks you see in the science fiction shows. Sometimes it really is just science fiction. So as informed voters, this goes for students as well as folks who are a little bit older like myself. We have to be able to come up with a smart policy on space, just like we come up with smart policies for everything else that the government is involved in. So that's a long way to go, and I just tried to sum up what the policy perspectives are going to be that you'll be hearing about. And the folks you'll be hearing from over the next hour or so are people who really know all this stuff inside and out much better than I do, and they're involved in the space effort, and they've been out there. Dottie has been out in space. Chris has been the flight director for missions to Mars. Roger has devised the rockets that can get us to Mars and get us all over the place. And then Kim Binstead will be joining us from Hawaii via Skype, and she's been involved in some of the simulation efforts where you put somebody in basically a tin can for 3 months or a year and you see how they work. It's kind of like Survivor, but in Hawaii, which doesn't sound so bad, come to think of it. So let me bring up our panelists. Roger Myers is Director of Advanced In-Space Programs at Aerojet Rocketdyne, and he's also the President of the Electric Rocket Propulsion Society, on the Board of Directors of the Electric Rocket Propulsion Society and the GenCorp Foundation, Chair of the Washington State Joint Center for Aerospace Technology Innovation. I believe you're going to be testifying tomorrow at a legislative committee hearing at the Museum of Flight about how Washington State should be involved in the space industry. So you can get it right from the horse's mouth right here. So Roger, welcome to the stage. Sure. And we might as well bring up the other folks, even though Roger is going to be the first one to speak. Chris Lewicki is President and Chief Engineer of Planetary Resources, a company based in Redmond. He likes to call himself Chief Asteroid Miner, because that's a lot of what this company is all about, is that they want to identify and mine asteroids for valuable materials. And you might think we're talking about gold and platinum, and there is a little bit of that in asteroids, but the really valuable stuff is water. If you're going to go anywhere in space, you're going to need water, not just to drink, but also to make rocket fuel and to extract oxygen from it for breathing and all the other cool things that you can do. So Chris is going to tell us how that relates to the effort to go to Mars, but he's got another side to his life story, that he was involved with the Spirit and Opportunity rover missions as flight director and was surface mission director for the Phoenix Mars lander. And those brought a wealth of scientific discoveries to our space effort, and we're still digesting all that. And so he knows the terrain almost literally when it comes to the red planet. So welcome to Chris. I'm going to mention a little bit more about Kim, because she's going to be next in our lineup, even though she's joining us remotely. She's Professor of Information and Computer Sciences at the University of Hawaii, and she's the principal investigator for a program called NASA High Seas. And High Seas stands for Hawaii Space Exploration Analog and Simulation. And so what they've done is they've created a habitat, just like a Mars habitat that you would have on another planet, and they put people in there, volunteers, to live there for an extended time. And if you go outside, you have to go outside under the conditions that you might have to follow if you were going to be on Mars, and you would eat the things that you would have to eat on Mars. And that's an important part of the research. One of her projects was to find out what kinds of menus work best on Mars, and how do people get along, what sorts of things are best for them to do to keep them occupied and keep them on track. And so Kim is going to talk about that. So look forward to that. And then our anchor anchor woman is Dottie Metcalf-Lindenberger. She joined NASA in the Astronaut Corps in 2004. She flew on the Space Shuttle Discovery in 2010 to the International Space Station and served as a robotic arm operator. And it was one of the longest shuttle missions ever flown, I believe. Up there, yeah. And then she went on to be the commander of a mission underwater. It's called the NASA Extreme Environment Mission Operation, NEMO, and it's in a habitat that's underwater off the coast of Florida. And so that's another experience where you find out what you're made of and learn how to get with people. So she retired from NASA, and now she's studying geology at the University of Washington and lives here in the Seattle area. So she's a local girl made good. Thank you. So I guess that pretty well wraps up my introduction, and now I'm just going to sit back and listen to what Roger has to say. Thank you.
So
Do you want to take
over
this?
here because I want to control the.
Yeah. And
It's probably easier. This is working. Yes, it is working.
What is your presentation?
I have no idea where it was put.
What's
Myers. It's the. No, it would be this one.
is this one?
Mm-hmm.
There you go.
And just tap.
And the clicker is.
Oh, the clicker. Okay, so I'll probably do this, and let's. Okay, so that works. I'll probably screw this up. I do rockets. I don't do AV. So thank you for at least chuckling at that. So let's see. We had an intro by Alan, and he really set the stage beautifully for, I think, all of us, because he talked about the balance of opportunity, risk, and money. Right? And when I say opportunity, it's the opportunity to go explore a new world and establish a human presence on that world. And so that's really what this is all about. It's about how can we do Mars exploration affordably within the budgets that we have and not go asking for astronomical sums of money. Before I start there, I just want to make sure that you all are aware that here in Redmond, Washington, is where we built the spacecraft rockets, the thrusters that are on every vehicle that you've heard about tonight. So we landed Curiosity on Mars. 7 minutes of terror video, who saw that? We built every engine that you fire there was built right here in Redmond, Washington. Who used GPS to get here? Every GPS satellite ever flown uses rockets from Redmond, Washington. So from our team. Who watched the Pluto flyby? That whole propulsion system was built in Redmond, Washington by my team. So we've been to every planet in the solar system. We're very proud of that. We're right now on contract for the Mars 2020 lander. And so we are really part of this community, as Alan was saying. So Alan also talked about how Mars is different than going to the moon. And let's see if I can, this is my first test and I will probably fail. Yep, I failed. How do I do this?
Oh, wait.
No? Ah, so then if this goes, it's the
no,
right
that's-
button.
Yeah. Oh,
No?
No. It's.
Oh, this. Okay. See, I told you I don't do AV. I'm also a Microsoft person, not a Mac person. So that should get some applause.
Slideshow. Then play from start. Then.
Okay, so now I do this. Okay, everybody, now you know. Okay, so why aren't we doing this now? It's because Mars is hard. Instead of 3 days to the moon and 3 days back and maybe spending a couple days on the moon, we're talking about it takes 6 to 9 months to get to Mars. And that depends on when you launch. So the orbits of Mars and the Earth, the orbital alignment determines how long it takes to get to Mars. But it's a long time no matter what. That means that the crew is going to be in zero gravity or in a high radiation field, and that's both solar and cosmic radiation for a long period of time. Okay, and there are two very different threat environments. That's how we talk about them, the radiation threat environment. In addition to that, of course, there's the zero G and the ability of the astronauts to actually do useful work when they get down and after they land. And there's the isolation factor, and you'll hear more about that from our subsequent speakers, from both Dottie and Kim. It takes 5 to 7 minutes for signals to get from Mars to here, and then 5 to 7 minutes to get back. So we're talking about long signal delays. So you can't have a conversation. It's not possible. So that's why when Alan showed that chart about being independent of Earth, that's what they're talking about. Any emergency, you can't have a conversation. The time delays are too long, okay? You also have to carry everything you need for that entire transit time. So all of the air that you're going to breathe, all the water, all the food, all the consumables for crew health, to maintain the crew's health. And if there are medical emergencies, you got to be able to deal with that, right? So that's just getting there. Once you're there, it's not a picnic. It's radiation, Mars doesn't have the Earth's magnetic field or the Earth's atmosphere. So even after you land on the surface of Mars, it's hard. Right? You saw a little bit of that in The Martian, right? Some aspects of it, okay? Frankly, they made it look pretty easy compared to the way it's gonna be, right? But you need all the stuff that you have in space, right? So that means you need a lot of stuff on the surface of Mars. And you have to get that all down to the surface of Mars, land there safely, and it has to still work after you land, okay? You got to do all of that within the budget that you have and for an acceptable level of risk, as Alan said. So that's the context. Challenges are enormous. But the cool thing is we have never been closer to Mars than we are today. We are making real progress. So how do we look at Mars? How do I, as a mission architect, as a guy who tries to think about how do I do all of that stuff within the budgets, right? Well, I think about it as a transportation problem. How do I make getting to Mars, landing, coming off of Mars? You can see here the different phases of the mission, right? Earth is over there on your left, and Mars is on your right, and lots of different destinations there. And so we look at it as a trade space, and we trade different launch vehicles, different rockets to get off the Earth, and different in-space propulsion technologies to look at what the implications are of all of these different options for crew and cargo transportation to get to Mars, and try to find the one that's going to be the cheapest system and yet manage the risk acceptably, okay? So what we found in this, and we found this several years ago and have been working with NASA headquarters and other organizations to help to partner with them to incorporate this into their plans, is you got to separate the crew from the cargo. That seems obvious today, but I'll tell you, 5 years ago, the risk of not having the astronauts on the way to Mars have absolutely everything they need on their journey, that was just unacceptable. Well, now they're starting to accept it. So it takes time to change cultures. So there's also, we talked about political will. There's momentum in just the way people think about going to Mars. And so we have now pretty successfully changed that and gotten, generally speaking, people accept the idea of separating the cargo and the crew. The next key step is to send the cargo efficiently using electric propulsion. So you use very high performance but slow propulsion to pre-position. You take all the landers and maybe the Earth return vehicles and all the food and all that stuff that you need on the surface of Mars. You take that a couple of years ahead of time. You landed on Mars, just like Mark Watney. Remember how the ascent vehicle for the next mission was already down? Well, that's the same thing that we're talking about doing now. So there are a lot of things about The Martian that I liked. The other thing, so pre-positioning assets on the surface of Mars is really an important thing from an affordability perspective. You can save a lot of money by doing that because, again, you can do that efficiently. Then you have to send the people fast using a high thrust rocket. So the logic of this is you take everything you possibly can off of the crew vehicle and you put it on the cargo vehicle so that you can shrink the size of the crew vehicle and get the crew there fast, get the astronauts there really fast. The other part of this whole thing about affordability is that if you build anything for just one application, it's really expensive, right? And so what you want to do is you want to build the rockets and the spaceships so that they can do multiple missions. Not necessarily reusing them, although that's great too, but having the same design go to the moon and building another one and going to Mars and building another one and going back to the moon. So just the production costs come down significantly if you have the same design working on multiple different things, okay? So that's one way that we think about, again, what we call a mission architecture framework of how do we do this affordably. I did that right. So what are the capabilities we need to go to Mars? We need to have a heavy lift launch vehicle, and there are a couple of options there that people are talking about. The SLS one that NASA is doing, and we hear about the Falcon 9. There's some different characteristics between the two that impact the way the in-space part of the mission is done. But there are a couple different options there. The Orion capsule, which launched last December, and let's see, where did all the rockets on the capsule come from? Redmond. They were built right here in Redmond, Washington. The big rockets were built in California by Aerojet Rocketdyne also, but I care about the in-space stuff because that's from here. Anyway, so you need a crew transportation vehicle, that's Orion. You need a heavy lift launch vehicle. You need a transit habitat, that's in the middle of the top. So you need a place where the crew can live for that 6 to 9 month transit time. And then come back, which is another 6 to 9 months. So we talk about 1,000 days of kind of capability. Then we need the propulsion system, the high thrust propulsion for the crew. That's the high thrust over here on your right in the middle, down below, and the solar electric for cargo. And then we need a Mars descent vehicle, a lander, and an ascent vehicle. So all 6 of those, you have to have all of those in order to do this mission. We're making progress on all of them, and that's what I'm going to talk about for the next couple minutes. So, cargo and logistics. Right now, we are baselining electric rockets for that, electric propulsion, and it's solar electric propulsion. Why solar and not nuclear? I get that question all the time. The reason is money. Solar is a lot less expensive. We can actually do this whole mission with less power than is now being used on the International Space Station. Okay? If we launch on the SLS launch vehicle, because it has a high energy upper stage. So we can do Mars cargo transportation with less cargo. For humans to Mars, we've done the whole study, so that we could do that with less power than is currently flying on the ISS. We are currently developing 13 kilowatt electric propulsion systems, 100 kilowatt electric propulsion systems for the next generations. Where NASA just finished a demonstration of a high power solar array, and we are doing some work in power system development. So this is, again, how does the spacecraft generate enough power to operate this propulsion system, this transportation system. And you do it modularly, the second bullet down here, so that you can do the multiple missions. So each module, you can use one module to go to the moon, and you put 3 of the same modules together and you go to Mars. Okay, so that's how you do the multiple missions from one design. Okay, so that's how you get the cost down. Okay, crew. Now I've got my cargo there. How do I get my crew there, right? The key constraint there is trip time, right? because you want the astronauts to be healthy when they land, right? And so you got to get them there fast enough so they're not hurt by radiation and that they're ready to work after 6 to 9 months in zero gravity. So you can't take 2 years to get your cargo. Can take a couple years. Your crew cannot. They got to go fast. So faster is always better, but it's very hard to go fast because of the orbital alignments, and it's very expensive. So that's why it's really important to shrink the size of the crew module, maximize the size of the cargo, which goes efficiently on solar electric propulsion, okay? That's how you get the crew there as fast as possible, most affordably. Now, I was just at NASA headquarters a couple weeks ago talking to the head of human health, of astronaut health, the group that is studying what the constraints are for long-duration deep space missions. And 6 months may be a constraint because of cosmic radiation risks. Okay? And you can't really shield against cosmic radiation. You can shield against solar. So they're very different threat environments, as I said earlier. There is a threshold in the sort of 6-month-ish range where people are very comfortable, the experts on crew health are very comfortable with trip times of about 6 months. You go beyond about 6 months and they get very uncomfortable and get very worried about astronaut health, okay? Now, if that constraint is relieved, there are lots of options for crew transportation. So if I can take 10 months to get to Mars with my crew, I have lots of choices. I can do lots of different kind of chemical rocket technologies that are flying today, no problem, right? But if I have to get there in 6 months, that's a much harder problem. We are trading right now, we're trading chemical rockets and what are called nuclear thermal rockets. So you can Google nuclear thermal rockets, and we actually had a big program in the late 60s and early 1970s, the NERVA program, and we actually fired some of those rockets back then, a very successful program. However, that technology it's not available today, and the environmental constraints and the ground testing requirements for nuclear rockets are very different today than they were in the late 60s. So nuclear rockets are great because they're very high performance. They're twice the performance of the best chemical rocket you can get, right? So a nuclear thermal rocket would be fantastic, except they're really expensive and they're really hard to test because they're nuclear. Right? So there are some risks associated with that. So chemical rockets are highly developed. They're ready to go, right? But they're not very high performance. So from an overall cost perspective, a chemical rocket to take the crew to Mars is going to need more launches, more of these big rockets that are very expensive, okay? So you can essentially do that sooner, but it takes you more launches. Nuclear thermal rockets, fewer launches, but more development cost. The nice thing about the nuclear thermal rockets is you can do a mission every 2 years. Because of the orbital alignment, the best time to launch an Earth to Mars mission and come back is once every 2 years, but there's actually a 17-year period, okay, that maybe Chris will talk about a little bit. Yes. I see I have 5 minutes. That dictates whether or not the rocket is actually going to be able to get there in the 6 or 9 months, right? That 17-year period. So the orbital mechanics are fairly complex. Bottom line of all of this is astronaut health and frankly their ability to stay sane cooped up in a small volume, as Alan was talking about, and I think Kim and Dottie will both talk about, on that 6 to 9 month journey and then on the surface and coming back. are going to drive the crew transportation options, and then the cost constraints are going to determine whether we go with chemical rockets or nuclear thermal rockets. Okay. I should say there's one other factor here, and that's something else that Chris will be talking about, and that is the use of local resources. So Chris showed water. Well, we all know that water is oxygen and hydrogen, right? And that's great rocket fuel. And if you can make that on, for instance, Phobos, okay, ahead of time, so say you send a robotic propellant manufacturing facility to Phobos ahead of time, and it makes tanks of oxygen and hydrogen, that may give the chemical rockets a real edge. Okay, so that's one of the reasons why we're very interested in the success in how Chris's business goes from a rocket fuel perspective. In situ propellant production, or you might hear in situ resource utilization. It's making stuff, living off the land. Okay. So now I've got there. I've got cargo there. It's already there, and I've got crew, but I have to get down to the surface. So I need a lander, and I need an ascent vehicle. I need to be able to come home. And it's really important to remember that, as I said earlier, on the surface, you have to have a place to live. Okay, you have to have your life support. You have to have all of your crew health systems. You have to have all your consumables, air, water, food, etc. Right? You got to have a power source to run all this stuff on the surface, right? And power on Mars, we're talking about a lot of power. It's not like the Curiosity rover or the thing that Mark Watney found that he dug up from the old rover. We're talking about a lot of power, many, many kilowatts, right? Probably 50 to 100 kilowatts of surface power that you need. And then, of course, you need to have all the equipment that you need to do stuff. So anyway, a lot of mass. Okay, so we're talking about landing 20 to 40 tons of mass on the surface of Mars. Curiosity, with all those cool rockets that we built, that was 1 ton. So we have to figure out how to land 20 ton, at least 20 times more than we landed with Curiosity on the surface of Mars. Okay, and then astronauts are kind of chicken, right, Dottie? They want to come home. And so we have to, yeah. So we need a launcher off the surface of Mars, and then they got to be able to come home. So, okay. So I talked a little bit about in situ resources. With the current projected, I don't care which launch vehicle you're talking about, as good as they get, we cannot sustain a presence on Mars if we take everything with us. We have to learn how to live off the land, right? And frankly, one of the things I'm most interested in is exactly that example I gave you, which is maybe we start a propellant production plant on Phobos. You could land on Mars with that fuel, and you could come back to Earth with that fuel. And that would really it would really drop the cost of the overall mission. We also need, on the surface of Mars, we want oxygen, we want water, and we want ascent propellant. The really cool thing is, in the Mars 2020 mission, we're actually doing the first demonstration of oxygen production. It's an MIT-led thing, so it's very appropriate to talk about here. The MOXIE demonstration of oxygen production. So that's coming up, and that'll be a big, big step for us. So overall, I hope I painted a picture of the need to, we've made a lot of progress. We have the cargo, everything for cargo is kind of in place. We have some trade studies we're doing for crew. We need to use, because of managing risk, we're going to do it using an evolutionary approach. We're not going to try to go straight to Mars the way some people like, because it's just too much risk. So we're probably going to go to the moon first, figure out how to live in lunar orbit outside that nice shield of the Earth's magnetic field. And then we're going to go to the Martian moons, and then we're going to land on the surface of Mars. So we're going to do this gradual phased program where we demonstrate the technologies and show that we can do it successfully. Okay? So where are we today? We have learned a lot from all the robotic missions that we've done. The radiation experiment on Curiosity has taught us a lot about Mars surface radiation. We're about to do the in situ production of oxygen using Mars 2020. We found water on Mars. I mean, that's a pretty big deal. So all of those things are from the robotic missions that we're doing. We're making a lot of progress on the big launchers, right? And the Orion crew vehicle. We have the programs in place for the solar electric propulsion for cargo. We're in the trade study space for the crew transportation. The nice thing is we probably don't need that until about 2030 when the first launch actually happens with crew. So there's a little bit of time to finish that development. And we're making real progress on the in situ resource utilization, okay? The big question, the outlier in all of this is the crew health constraints. What are the trip time requirements for the crew? That's gonna drive whether or not we can, what kind of propulsion technology we need, how big a habitat we need, how much stuff we need on the surface of Mars, and that's going to determine the overall economics. Is it affordable? I personally am really excited by the progress that we've made as a nation and frankly as a planet, as a species. I think Mars is within our reach. So I look forward to hearing the rest of these.
All right, good evening, everyone. Happy to see a lot of familiar faces, the Seattle space fans in the audience, but also pleased to see a bunch of new faces in the audience. Always good to share the joy of what we're working on. So I'm going to talk a little bit about my life on Mars, such as it was, and the focus we've had on resources, which ultimately can help us get to Mars, to the moon, to asteroids, and anywhere we choose to go. So this little creature in the middle of the picture here is Opportunity. And is this a laser pointer or no?
I think so, yeah.
Possibly. Well, no, that's going to do blind.
It's risky to use that.
I don't think it's a laser pointer, actually. So I'm on the left. Chris Voorhees is also on our team, is on the right. Opportunity is in the middle. That was the first and last time we drove it on Earth, a total of about 60 feet at Kennedy Space Center. And if you look very closely, you can see Spirit up on blocks in the background. So this is when we were putting them all together at Cape Canaveral in Florida. So going from Earth to Mars, this is where Opportunity ended up. And this certainly is a vista I'd love to see with my own eyes one day, or at least a higher definition camera. This is Marathon Valley. And after dozens and dozens and dozens of kilometers that Opportunity has driven throughout its lifetime, Opportunity and Spirit were a series of Mars missions, as Roger was talking about, following the synodic period of Earth and Mars. Every 26 months we get a chance to take kind of the easy trip to Mars. It's kind of like catching the bus when it's out front. And any other time you want to go to Mars, you have to chase like 5 city blocks or maybe halfway across the city before you can catch up to the bus. So we went for almost 20 years from first missions to Mars and landing on the surface of the Mars in the 1970s with the Viking missions till we landed Pathfinder. We followed that again with the Twin Disaster Pack, Mars Polar Lander and Mars Climate Orbiter in 1998. And because of that, we didn't go to Mars in 2001, kind of broke the streak. We were actually building what ended up being the Mars Phoenix lander during that time period, but decided not to launch it. So Spirit and Opportunity followed the water, so to speak. They were looking for evidence of water and aqueous-based processes and mineralogy on Mars, and they certainly found them, especially Opportunity and Meridiani Planum in the areas that it landed. Phoenix, Mars Phoenix, which was a fixed lander, went to Mars really with a single goal, and this was based on orbital assessment on Mars of the gamma ray spectrometer. They found a high presence of hydrogen, And it's a lot easier to detect hydrogen with various techniques than it is to detect oxygen. So what else could a lot of hydrogen near the poles of Mars be connected to other than perhaps a lot of oxygen? So we wanted to go there and find out, and dug a bunch of holes and trenches on Mars. And before Mark Watney appeared in theaters this year, this was one of the earlier times when we took pristine, really expensive NASA hardware and got it really, really dirty as we proceeded to take all that Mars soil and dump it into the thermal and evolved gas analyzer in the wet chemistry laboratory. Mars Phoenix really confirmed by direct measurement and direct manipulation the presence of water ice on Mars. And this is up near the North Poles, near the Arctic Circle on Mars. Just like Earth has an Arctic Circle, Mars has a similar thing based on its axial tilt and its orbit around the sun. And in those places, solar-powered rovers don't do so well when it gets into the winter. So Phoenix's mission lasted 152 sols and then was over, but we left that mission knowing for certain that at least in certain areas of Mars, we only had to dig down a few inches to get to ice. And unfortunately, that ice is so cold that it has the same compressive strength as concrete. So you better bring a drill with you. So Curiosity continued to follow that path, and here are the very famous pictures and self-portraits that Curiosity has with its long arm out in front of it. And it is climbing Mount Sharp, and it has found more and more evidence that Mars was once a very, very wet place. But I think what we're learning about it is not wet in the way that we kind of understand and familiar with the oceans on Earth. It's kind of wet in the way that the salt marshes in swamps in the brackish areas of Earth are, maybe after they've drained out for a little while. So you get these seepages of very salty, briny water. Sometimes it's only on the surface for a little bit, but even on Earth we find life in those portions of kind of the biome here on Earth. And we want to take sensors to Mars so we can find those same things. And this year, even more exciting now, there's been evidence found that not only is there ice on Mars, not only is there evidence that there once was on Mars, but really on an annual basis, there is water and Martian ice. I can't say subterranean because that relates to the Earth, so it's sub-aeolian, I think, is the proper term. Ice that melts and kind of seeps out these crater walls, probably immediately evaporates, leaves kind of these white deposits, things like we're seeing in the asteroid series. But if you are a Martian traveler and you don't want to do the dangerous things that Mark Watney had to do with hydrazine to try and produce water, there's water on Mars, if you can use it, if you can collect it there. And this is really something that Roger was talking about, is we will get to a point in space in the future where we will make strong use of local resources. And the first and most useful resources is that simple one of water, 2 hydrogen atoms and 1 oxygen atom. It certainly is useful for keeping all us alive, and it's useful for growing and raising the things that we need to keep ourselves alive. It's also useful for manufacturing, for industrial processes. We don't think about water as a solvent or water as a fluid device that helps us transport things, but if they say you can go without food for a very, very long time, but you can't go without water for very long at all. So water is also important in that, as Roger mentioned, it's rocket fuel. Even if you don't use the hydrogen part of it, oxygen is an oxidizer in any chemical reaction, whether you're using perhaps methane derived from the atmosphere of Mars as your fuel, or you're using hydrogen. Or even things like we use, you can use rubber tires as fuel, but oxygen you need to catalyze that reaction. Something that when you get into the chemistry of things is very interesting to learn is everything that you send into space, every kilogram of material needs another 50 kilograms behind it. Even if that kilogram of material is fuel, you need 50 kilograms of fuel to send it there. And if you think about that fuel as being oxygen and hydrogen, most of the mass of that fuel is the oxygen, with a higher atomic mass. So if we could just start with getting the oxygen from space, that really is 80% of the mass of these chemical reactions that we're dealing with, and something that's very, very important to us. And I will challenge one thing that Roger said. We'll get into the controversy tonight. He mentioned you can't shield yourself from cosmic radiation, and that's true, unless you have a few $billions of water per astronaut in terms of transportation costs. And that's why we don't do it, because it's prohibitively expensive for every individual. For Dottie going into the space station, if she had had the luxury of staying up there for 6 months, which I'm sure she would have loved, the near longest mission to be the record-setting longest mission, like the year in space that we're going through now. But a ton of water for every 6 months for every person in space, and this is assuming that you're recycling most of it, but there's losses of it, and there's, of course, all sorts of other uses of it. But if you can get it from space, it now starts to become a resource, whether it's a resource for radiation shielding, for propulsion. So it's just a very important thing. So this is something for folks who haven't been through rocket science education, or haven't taken orbital mechanics, or don't really have that visceral feel for the world out there and what space travel truly is. The first 9 minutes of getting into space is that violent journey on top of the rocket from Redmond, and they'll get you there, and it'll be quite a ride, but you expend an enormous amount of energy. And once you've got there, you're in low Earth orbit, a wonderful place. You see our beautiful planet. Go another 20,000 miles, you'll be in geosynchronous orbit, where we get a lot of our satellite services from, whether it's television or network services or weather. And then we see all these other things in space is very, very far away relative to low Earth orbit. But if you think about the amount of energy that you have to put in, how much fuel you have to put into the gas tank, how fast you have to get going kind of to get up to highway speeds, what you actually realize is that Earth is far away from all of those things in space. And once you're in space, you're actually pretty close to everything else. Actually, as Robert Heinlein says, once you're into low Earth orbit, you're halfway to anywhere in the solar system. And to kind of counter this point, as we were passing by with the New Horizons missions going past Pluto this summer, if you had put the same amount of energy into the space shuttle that it received going from Florida to low Earth orbit, you put that back into the space shuttle in low Earth orbit, you could be going past Pluto. You know, you'd have all kinds of other technical problems. But from an energy standpoint, this really just shows the point that once you're in space, you want to try to keep everything that you got there. You want to use it for as many uses as you can, and you want to try to top it off and refuel it. So let's transition a little bit to our kind of celestial neighborhood here. We've got Jupiter, we've got a little blue spot there on the left is Earth, the red dot is Mars. Most people think about the asteroids being out in the asteroid belt between Mars and Jupiter, but there are actually a number of classes of asteroids that cross the orbit of Mars. Some of them cycle back out and forth between the asteroid belt and here, and some of them are actually quite close to home, and these are what we call the near-Earth asteroids. And they have all sorts of useful things on them, not only water, but construction materials that we could use to fuel the Iron Age, so to speak, of space, so that when we're building future structures, we could actually have foundries in space. Not things like you'd see with the blacksmiths on the frontier, but probably things that more closely resemble a 3D printer. Technology which we've actually already seen demonstrated on the International Space Station and is continuing to accelerate. So that is what my company is really looking at, is creating not only the scientific knowledge of there's water on Mars, there's a bunch of resources, everything that we need actually to go there and stay is there in some abundance, if only we had the technology and kind of these systems that we need to kind of establish that beachhead. So we're working on the sensor systems that we can go to asteroids, which are among the most accessible places we can go, characterize those resources and understand really how to use them, starting kind of in the zero gravity environment of space and then moving to where that will take us. And this is something that I think a lot of people don't realize. There's already been a lot of work in this area. Here is the asteroid Itokawa, which is a small near-Earth asteroid the Japanese went to. This is just a lump of rock. But let me show you another asteroid. This is a D-type asteroid. It's tens of kilometers across. It is very loosely held together, and as a D-type asteroid, it actually might have a lot of leftover phyllosilicates, hydrated minerals and water and things like that. And this particular asteroid happens to be orbiting Mars. So this is Phobos, which was mentioned earlier. And I absolutely love this picture of Phobos. A lot of times you see these pictures out of context. You see this gray surface and you can't really tell kind of the color of it. But this is, kind of Mars in the reddish gray background, and what you see is what is a 4% reflectivity, which is a little bit darker than a piece of charcoal that would be in your barbecue grill. But this is what's up orbiting Mars that might actually be ours to leverage. So in a lot of ways, this spot in the solar system is every bit as accessible as a near-Earth asteroid is in some ways easier to get to than the surface of Mars or the surface of the Moon because of all the gravitational advantage that we can get out there. So we look forward to creating the spacecraft. We launched our first spacecraft from the International Space Station this summer, the Arcade 3. We're working on our next satellite, the Arcade 6, and we have on the Arcade 6 infrared imaging technology, the first commercial deployment of this technology in space so that we can actually measure the contents of water in things that we look at. And we're actually out testing this instruments and technology today off of airplanes, kind of looking at all the things that we can use to calibrate it on Earth as we deploy it into space. This is something so that we know if we can take good images of the Earth and we can detect water and activity in its various forms, we can find that in space as well. And over in Redmond, this is our spacecraft coming together. We're doing a lot of tests on it this week. But this is something that I think we can really change our perspective on using these resources to actually help us get out of low Earth orbit, get into deep space, get there to stay, and keep building up a presence. And as just kind of a final point on my comments, ultimately this is all about resources, but the most important resource in space is going to be us. And when we're up there, we of course have a lot of needs and a lot of demands, and as we've found on this planet, we can get a lot of that stuff in locally, and that's the same is going to be true in space, and we look forward to creating that economy. Thanks.
Kim, are you on the line?
Yes, I am.
Okay, perfect. All right. I gave you a little introduction, and so please tell us all about simulating trips to Mars and what's involved.
Well, okay, I can do that. But I think there's a recorded lecture that's all ready to go.
Okay.
Thank you so much for inviting me to speak to you today. I'm sorry I couldn't be there in person, but I've recorded this presentation and I'll be there remotely to answer your questions once it's over. I'm going to talk about the HI-SEAS project. HI-SEAS stands for Hawaii Space Exploration, Analog and Simulation. And it's a NASA-funded project at the University of Hawaii with a large team spread out all over the world. HI-SEAS is an analog environment. And what I mean by analog is a place or a situation on Earth that is similar in some interesting way or ways to a place or a situation in space. So I'm particularly interested in Mars analogs. And a Mars analog would have some key features in common with Mars. Now, there's no perfect Mars analog because, for one thing, it's very difficult to set up an environment that mimics Mars gravity. And no environment here on Earth is going to be as remote or as cold or as hazardous as Mars itself. But analogs do share some interesting features with their targets that allow us to do useful research and useful testing. So, for example, we use analogs to discover problems and to test solutions. There are some problems that you just don't really see until you have tried out your equipment or tried out your procedures in a long duration analog. We also use analogs to design in the context of use. And what I mean by that is that there's a very common practice, particularly in software engineering, where if you want a really good piece of software, you just don't tell your crew to just go sit in a room and think really hard. You send your software development team to the environment it's going to be used in. So, for example, if you're designing medical record software, you would send your team to a doctor's office where they would observe how the paper records are currently being used, who uses them, how each of the users uses the record, and so on. It's a really good practice and it leads to better performing software. However, it's obviously pretty hard to send software engineers or other designers to Mars, of course, before the astronauts get there. So how do you allow your team to design in the context of use? Well, you can send them to an analog environment where they can at least get a feel for what the actual Martian environment is going to be like and how their piece of software, piece of hardware, or procedure is going to be used. We also use analogs to integrate people and systems in realistic scenarios. So here's an interesting looking analog. This is Pavilion Lake in Canada, and obviously it's not a very good physical analog for Mars. It's full of water. But instead what you see here is an astronaut in a one-man submarine, an autonomous underwater vehicle, and a scuba diver. So the astronaut in the submarine is working in a similar way to an astronaut in a rover on a planetary surface. The autonomous underwater vehicle is working in a similar way to an autonomous rover might on Mars. And the scuba diver is working in a similar way to an astronaut in a spacesuit. So here, these three very different ways of working have to all work together. And so we can learn by these integrated scenarios what works and what doesn't. So after having seen a bunch of other analogs, this is HI-SEAS. It is a 36-foot geodesic dome at about 8,000 feet in the saddle area of Mauna Loa on the Big Island of Hawaii. And you'll see right away that this is not the Hawaii that features in travel brochures. It's very, very stark, it's quite cold, there's no plant or animal life, and it really physically looks quite similar to the surface of Mars. If there weren't the white clouds and the blue sky, this area looks very, very similar to the images that are sent back by the rovers on Mars. It's completely off the grid. It has to be. It's nowhere near any services, so power, water, and so on are all off the grid. It's also very isolated from human activity. The only real human activity you can see from the site is the telescopes up on top of Mauna Kea, which you can see off here, maybe that little tiny white dot off in the distance. And you can sometimes at night see a few lights from the town that is over the other side of this ridge here. But really, you don't see any human activity from the site, so it's very visually isolated, which is one big advantage. Another advantage of this site is that it's actually, despite being visually isolated, it's quite accessible. And this is good for a couple of reasons. One is it means that we can go to the site and take away, for example, biological samples that need to be tested in a laboratory. It's also good because if our crew members get injured or get sick, we can get them to a hospital fairly quickly. Now, you might say, wait a second, you can't get someone to a hospital quickly on Mars, and you're absolutely right. This adds a layer of safety for our subjects, which in turn allows us to ramp up the simulation quite a lot. It means we can mess with them more, to be honest, and that's good. It means that we can ratchet up their stress levels, we can ratchet up their work levels in a way that we wouldn't be able to do in a simulation in, say, Antarctica. So, why is NASA interested in the kind of research that we can do at HI-SEAS? Well, to understand that, you need to know a little bit about how NASA assesses risk for long-duration spaceflight. For any given mission, they have a fairly long list of risks, and those risks are organized into green, yellow, and red. A green risk is one that we have under control. NASA's confident that we understand it well enough and we've got enough countermeasures in place that it's not going to be a problem. A yellow risk is one that isn't completely under control, but NASA has assessed that either it's unlikely enough or it's not so big of a problem that they need to continue to work on countermeasures or ways of alleviating the problem. And then there are the red risks. NASA will not fly a given mission if there are still red risks on the list. So our job as researchers is to retire as many of those red risks as we can in order to enable NASA to fly a given long duration mission. Now, some of those risks are not addressable in the high seas environment. So, for example, risks to do with microgravity or to do with radiation. High seas has normal Earth gravity and normal Earth radiation, so it's not the right place to be looking at those risks. But there's a bunch of risks that have to do with crew performance, crew psychology, remote medicine, procedures, communication systems, and so on, that are very good to evaluate in an analog environment like high seas. And high seas has certain advantages. One is we are able to pick an astronaut-like crew. That's unlike, say, research stations in Antarctica where the crew members are selected for their ability to do the work that they're having to do in Antarctica. So, as you might imagine, astronauts have quite a different psychology from your average man on the street. So it's really important to have a crew that is as similar as possible to the astronaut population. We also give our crews very similar work to the work that an astronaut crew on Mars would have. Similar work levels, they're doing similar things during the day, and so on. Similar command structures. Also, we're able to do very long duration studies. These are harder to do in places like Nemo or Antarctica just because of the very challenging logistics. But at our site, because of Hawaii's mild climate, we basically have the same conditions more or less year round. And that allows us to do these very long duration studies. As I mentioned before, the site allows both crew isolation and easy access by the researchers, which is a really nice balance. And because it's an analog specifically designed for this kind of research, the researchers can control all of the various mission parameters. So, for example, if a researcher wants to understand how lighting affects sleep, we can change the lighting. And that really helps to make the research strong. So here's what it looks like on the inside. As I said, it's a 36-foot geodesic dome. The downstairs has the kitchen. It has a large common workspace which can be reconfigured into, for example, an exercise area or a recreation area, depending on what the crew are doing. There's a dining/conference area where the crew have their meetings and eat their meals. There's a laboratory which has some basic equipment in it so they can, for example, analyze biological samples. There's a bathroom downstairs. Now, I should just point out that the water is extremely limited, as it would be on Mars. So the toilets are composting toilets, non-flush composting toilets, and the crew are allowed only 8 minutes of shower time per person per week. I should also point out that our crew, being astronaut-like, are always trying to improve their performance, and our current crew have limited themselves to 3 minutes of shower time per person per week. The upstairs of the habitat only occupies half of the dome, so that some of the lower area has the high ceiling of the dome. And it's primarily a sleeping space. Each crew member has a very small pizza pie shaped bedroom with a cot in it and a small desk, and they do have doors that can shut, so that's an important piece of privacy for our crew. And there's a second bathroom with a toilet upstairs. Of course, we are tracking pretty much everything that goes on in the habitat. We're monitoring, of course, power levels and water usage, the weather. There's a weather station at the habitat, but also things like CO2 levels and temperature and so on. So all of that, it's all data. Communication is interesting. Because of the distance between Earth and Mars, the time it takes for a signal to get from one to the other is limited, of course, by the speed of light, and varies from a few minutes up to more than 20 minutes. We are simulating that with our crews by having a 20-minute each-way communications delay. And of course, this means that they can't just pick up the phone and call someone, because the time between saying hello and hearing hello back would be 40 minutes, taking into account the 20-minute each-way delay. They're also not able to surf the internet for the same reason, because each click would take 40 minutes. So that means their primary mode of communication is by email. Now, they can do things like record video, record audio, and send that. And they do that, but mostly we use text email to communicate with the crew. They are allowed to go outside, but only in the spacesuit and only in a group. It's a minimum of 2 people on any EVA. EVA stands for extravehicular activity, and it's NASA-E's for going outside. So they have to wear their spacesuits, they have to submit an EVA plan for approval the day before, they have to be monitored from inside the hab for the duration of the EVA, so it's certainly not a way to relax and get away from it all. And on these EVAs, they do a couple of things. One is they maintain any of the habitat systems that are outside, such as the power systems, the water tanks, and so on. But they also explore the area around the habitat and do geological tasks. So, for example, we get them to map out the lava tubes that are in the area around the habitat. Lava tubes are quite interesting. We're fairly sure that there are lava tubes on Mars. And we're interested in them for a couple of reasons. Primarily that they would make an excellent radiation shelter. Why are we interested in radiation shelters? Well, one is just in case our crew need shelter from radiation, although some radiation protection would presumably be built into the habitat. But also, one of the reasons to go to Mars is to look for signs of past, or even, cross fingers, present life. And presumably that life would also need to shelter from radiation, so lava tubes might be a good place to start looking. To date, we have done 4 missions. The first one was actually primarily a food study, and that was part of another grant funded by NASA. And then the next 3 were all on the current grant, and they all have to do with crew psychology. So you can see here, starting on the left, this was the first missions patch, and as I said, it was about food, which of course you can tell by the spork. And then these 3 missions went together. High Seas 2 was 4 months long, High Seas 3 was 8 months long, and we're currently 3 months into High Seas 4, which is a full 12-month long mission, which is a pretty significant commitment, as you might imagine, by the crew members in question. This is what about 4 months of shelf-stable food looks like. Because refrigeration takes up space and power, food for long-duration space expeditions basically has to be shelf-stable, and that means dried or freeze-dried to the most part. So our crews actually eat very well. We give them as much as we can that meets those criteria, so we give them freeze-dried meat, freeze-dried vegetables, freeze-dried fruit. And generally speaking, they've been pretty happy with the food that they've been able to prepare from that. Now, I mentioned that the first mission was part of a food study, and the High Seas part of that food study was comparing 2 different food systems. One is the food system currently used by NASA, which is primarily individual dishes that are individually packaged and are just heat and eat or add water and eat type items. And we're comparing that with something that's a little bit closer to cooking. Now, of course, you can't cook on the space station because it's with the microgravity, you can't keep the ingredients in a bowl, which makes it very challenging. But on the surface of Mars, there's enough gravity to keep the food down, and that enables a certain amount of cooking. So in comparing those 2 systems, the advantages of going with shelf-stable ingredients that can then be cooked is there's much less packaging, it's much easier to keep the items shelf-stable when they're in bulk, and the fact that the crew can mix and match the ingredients means that you can get a lot larger variety of food out of a relatively small number of ingredients. And To think about that, you might imagine that a pre-prepared lasagna might be very good, but it's a lasagna now and it will always be a lasagna. Whereas if you give someone pasta and tomato powder and cheese powder and herbs and spices and maybe some freeze-dried meats and vegetables, those can be combined in many, many, many different ways to produce a lot of different dishes. Now on the downside, when you're cooking, you require time to cook, you require energy to cook, you require more equipment to cook. So there are pros and cons to both systems. And essentially we were giving NASA the numbers it needs to decide what combination of those systems to send on a long duration spaceflight. So here are some of the other activities that our crew get up to. They are of course exercising. They're taking pictures out the one small window that they have to see to the outside. And also we try to get as much research done as possible in addition to the central funded research, because if you're going to stick people in a habitat for 12 months, you want to get as much data out of them as possible. So in addition to the central research, at any given time they're doing half a dozen to a dozen other research projects. This is what we call opportunistic research. So on the left is an example of opportunistic research on the current mission, which has to do with, this particular project has to do with 3D printing surgical instruments. And on the right is an opportunistic research project we unfortunately had to reject, which was using mealworms as a source of protein in the diet. You might be surprised to learn we didn't reject it because it's gross. We rejected it because we discovered that mealworms are little escape artists, and the habitat's in an environmentally sensitive area where we didn't want to risk introducing any invasive species. So what are some of the things that we've learned? Well, we're not yet at the end of the 3-mission cycle for the crew psychology study, but we do know some things. And one thing is that astronauts, they're pretty stoic folk, and they are fairly optimistic people. And those are both very good traits. Unfortunately, it tends to mean that some problems will go a while before they are officially verbally reported. So if you ask an astronaut how they're doing, they will generally be pretty positive in their response. That's all well and good, but on a long-duration space mission, you really want to know about any potential problems as early as possible, maybe even before the astronaut's aware of them themselves. So one of the prime research themes that we're currently working on is about passive monitoring. How do you tell whether something is starting to bubble under the surface that might turn into a real problem? We do this in a bunch of different ways. For example, we have a study from Michigan State which has the crew wear sociometric badges. These badges measure the proximity between any two crew members. And although it doesn't record what they're saying, it does record the volume of their voices. So you might imagine if it detects two people are standing very close to each other and the volume of their voices are very high, they might be having a fight. Or if two people never get near each other, then they might be avoiding each other. And those are the kinds of yellow flags that might cause mission support to look into it a little bit further. We've also learned a bit about control and autonomy. Right now, NASA has a very fine level of control over everything that goes on the space station. The space station is flown from the ground, and the astronaut schedules are scheduled down to the minute. That's simply not going to be possible on a Mars mission. One, because of the length of the trip, 2.5 to 3 years return, depending on the mission profile, but also because of the communications latency that I mentioned earlier. If it takes 40 minutes for a question to be asked and the answer to be sent back at a minimum, the crew are simply not going to be able to be controlled in the same way that the ISS crews are now. And that's going to necessitate crew autonomy, a certain amount of crew autonomy. Now, NASA's structures are simply not set up for that right now. So some of the things that we are learning and telling NASA about are about how to allow the crew more autonomy without reducing their safety and effectiveness. And finally, we're learning a lot about cohesion and performance. Team cohesion is, we know from years of research, it's very positively correlated with performance. The more cohesive the crew, the higher their level of performance. However, it isn't without a downside. A highly cohesive crew is going to be very high performance, but they're high performance on the tasks they choose to do. They tend to trust their own judgment more, and there is some tendency to go their own way, shall we say. So there's some concern of not out and out mutiny, but of crews straying from the mission plan that NASA would like them to follow. So we're learning a lot about that trade-off. Finally, we spend a lot of time doing education and public outreach projects. Our crews are very involved with that. They send materials to schools, they answer questions from students, and they're generally very enthusiastic about that kind of thing. They all keep blogs. And so I do encourage you to go to our website, which is hiseas.org, hi-seas.org, and there are links there to all the crew blogs, and I think that you'll find them very interesting. Very much for your time today. I really appreciate it, and please let me know if you have any questions. I'll be on Skype to answer them.
Thank you, Kim. I'd like to ask you, Kim, to hold on for a little bit because we'll have Dottie Metcalf-Lindenberger, who has actually been in space and not a simulation, talk about the challenges that are very similar to the challenges you've been studying, and then we'll take questions from the audience. So Dottie, please take the stage.
Gladly. All right. Make sure. And it's back underneath, I think. Well, good evening. It's great to be here with you guys. I'm a former high school teacher, so I tend to wander around a lot, so I'm just going to come out here a little ways so I can step out and see you. It's great to have such a mixed audience tonight, too. I'm also really encouraged to see young people in the crowd because I think that you guys have a great opportunity of being on the surface of Mars. So as we get ready to look at what I'm going to talk about this evening, it's first I'd like to start out with the tradition that we've had at NASA of training and what I think will stay the same and what things I think are going to change. And then I'm going to kind of break halfway through and we'll go to the analog that I served as the mission commander for NEMO and talked about what we did there that is similar to some of the asteroid mining that was being done. We were looking at visiting near-Earth asteroids and then also thinking about what you can learn as you go on and do things like what Kim's doing with HI-SEAS. So first of all, something that is not going to change at NASA, and I think it's because it's very important, is our flight training. And we start out as astronaut candidates. After I was hired in 2004, you can see me there on the left-hand side in the background. Chris Cassidy, who flew on both shuttle flights and to the International Space Station, is now the chief of the office, and I are in the front of a helicopter pit that is going to be dunked into the water, and it's going to flip over, and then we're going to escape blindfolded. And so we did this 3 times in our early training, and it's good, first of all, because you're going to be flying aircraft around while you're doing your early training as an astronaut. And it right away solidifies you as a group. You're all helping each other to do the very best and perform the very best that you can in extreme environments, which is what Mars is going to be like. So we're going to keep flying aircraft and we're going to keep training. And some of the other things that you do while you're in Pensacola, of course, is to be in other water environments and see how you could get out of your aircraft and get out of your parachute, not let it drag you down, etc. Well, we do this because we fly in the T-38. And the T-38 is a great training aircraft because it has a pilot up front and a mission specialist in the back. And currently, we're looking at even incorporating the T-6 as a plane that we could teach mission specialists to fly out of Pensacola, where then someone like me who didn't have an aviation background could learn how to fly this aircraft and go out with another mission specialist. But for the time being, we're using the T-38, which is flown by our jet pilots. And this is real-time training all the time. You can get into a T-38 pretty much any time of the week except for when there's really bad weather over the Gulf, which might be a lot of the summer there. And you take it out and you're using checklists. And so, of course, you do that early pre-flight work where you've looked at the weather, you've looked at where you're going, the options for if something goes wrong, and then you head out. Now, granted, when you're going to Mars, you're not going to have the option to get out of this situation, but you are going to be using checklists and you're going to be thinking about these real-time decisions that you've already practiced making over and over while in Houston. Another thing that is not going to change, that's going to be very important as we go to Mars, is knowing your vehicle. So I had the opportunity to train on the space shuttle and learn about all the 1,500 switches and circuit breakers that ran that machine, all of the systems, and granted, they had been built about the time I was born, so they didn't operate exactly as I expected, but it was a fabulous vehicle and it did many things for us, and we learned early on how the basics of that vehicle worked, and then how it worked with simple malfunctions and then with complex malfunctions, all while either working individually so that we knew we could do it ourselves, or while working as a team so that we knew that the cohesive unit could solve problems, which included the ground. Now, as we've talked about with Kim, that's not always going to be available because of the time latency there. And so we have to be able to operate things on our own. And knowing your vehicle is very important. Look at what Mark Watney was able to do because he knew it so well. And some of these things you know about your vehicle, you don't need to know at that very minute all the time. So I think there can be things stowed on board where there may be a complexity that you could go research on your way there. And that's going to be how they design the vehicles. And then you're going to need to know your suits. And there will probably be one, probably two, maybe even more. And so the suits that you launch in are probably not going to be the same ones that you go out for your spacewalks in, although maybe they will. I don't know. That's still to be determined. But you have to know this other, essentially aircraft, because it is your life support. It is what keeps you safe. It is what will allow you to go out and come back in. And it works to provide you oxygen, to scrub the carbon dioxide, to keep you warm and to keep you cool, to have communication with the people that will be inside the habitat while you're out doing spacewalks. I don't think that we'll all be out away unless we're going to a vehicle that we're going to be launching from the surface from, or we're just arriving. So there's going to be all these systems, and it's really important that you understand how they work before you leave. And finally, you've got to know each other. And this is something that we do through the National Outdoor Leadership School, better known as NOLS. Early on in our training at NASA, we went for a 2-week backpacking trip in the Wind River Range in Wyoming. And during this camping, you get to know and talk about a lot of the things that are important for survival in the future. It's a little bit of an extreme environment, although not that extreme. Most of us were backpackers and hikers before we showed up at Johnson Space Center. But the good thing is that you're out away. You don't have water with you all the time. You have to go collect it. You have to treat it. You have to think about what you do with your waste. You think about the food you're taking, how much you can consume, how do you need to stretch it. We had an emergency arise while we were out. The Hurricane Rita came in and our families were having to evacuate. And so we actually had to leave the field early. And so on a day that we had already walked quite a long ways and set up our tents and thought about going to bed, we broke down camp and we hiked another 4 miles to get that much closer so that we could get out of the wilderness earlier and be with our families. So it's a great place to start to learn about yourself, to think about those things that you want to talk about before you're going to go on the mission and be in a small confined place together for a long time. So that's what I think is going to remain the same about NASA's training. And then I'm going to talk about, and before we cut that out, you're going to take your family with you. And as Kim said, the great thing about the the way that you can live in near real time is that you live in near real time all the time on your cell phones and iPhones. You don't respond to texts necessarily immediately, but you might in the next 5 to 7 minutes. Or that email that you get from your boss, well, if you were asleep last night, you can still respond to it in the morning, and that's soon enough. And we do that all the time, and we'll do that with our families and our friends, and we'll take them with us. And I had a chance to do that even while I was in space. I made a video that just this year I showed my daughter, who's in the back of the room now at 8, because when she was 3 years old, she wasn't quite ready to understand what was going on in it. And it still has meaning to her, maybe more meaning now that she's 8 and not 3 years old. So you'll take your family and your friends and the public with you on this amazing adventure. So now onto the analog I had a chance to be a part of under the water off of the coast of Florida. And this was NASA Extreme Environment Mission Operations, better known as NEMO. We were NEMO 16. And our mission had the purpose of understanding how we would work at an asteroid and maybe sample it. This is early on, very preliminatively worked out. And we were working under a communication delay of about 100 seconds because near-Earth asteroids are not that far away from us. So when we headed down, we first had done some initial training back at Johnson Space Center, and this same equipment could be easily adapted to work with conditions for Mars. So Mars, you're thinking about a third of the gravity here on Earth. So of course you can stand up and walk around and put some things down, but you are going to be leaning a little bit differently and carrying things just a little bit differently. And so this is a chance to think about that before you go out and do those missions. It's also a chance for the people that are building that equipment, and that's important. They're building now and thinking and planning now. They can start doing that as they go. Then we went to Florida and we did another week training. So I had never done helmet diving. I had I'd been diving for many years, especially in the neutral buoyancy lab. That's our big swimming pool for the space station training. But I had never had this chance to do this. And so the great thing about astronauts is that they love to learn, just like this audience. You guys love to learn, you're curious, you never want to stop learning, they're lifelong learners, and I think that's just going to be even more important as we go and select our crews. So we trained up really quick on how to do this helmet diving, and I enjoyed working with this crew. You can see Kimia Yui, he's currently on the International Space Station serving JAXA, and myself, and then Tim Peake will be flying in a couple of days here. He's a British astronaut. And then Steve Squires, who is at Cornell and does the research with Spirit and Opportunity. So it was a great crew. We had only done those 2 weeks of training together. And that's what I think is so amazing about space, is that it brings together, and I think it will continue to bring together, international cooperation. Well, this is where we live together. It's underwater. It's about the size of a school bus. You have to go to the bathroom outside in that little white cupola. If you want to know more about that, I'll talk to you about it later. And it is a place that you could leave, but you can't leave easily because you are underwater and now you're at saturation for diving. So you can't just leave. It takes a 16-hour process. And if an emergency did arise, we could go, but then we would have to immediately go into an air chamber on a boat. So it does have a very real sense of risk while you're there. And you can see us outside around our kitchen window. Windows, as Kim mentioned, are very important to crews. We love to look outside. I think you probably are the same way. And then this is our control room. So this is where all of the air and all the different systems we're working out of. And this is the first time I didn't get to know my vehicle really well. We had 2 habitat technicians living with us. And it is a little bit disconcerting not to know your own vehicle well, because halfway through our mission, they ran some emergency scenarios on us. And when you don't know where the tools are, it can feel weird. And when you can't talk to the ground right away because you're on a delay, you can feel isolated and wonder, why don't I know how to solve this problem? So again, this makes me think that a lot of our training will start to go to do-it-yourself type of opportunities. I think we will launch a lot of information and videos and manuals that are already compressed on our lovely digital computers, and that we will be able to figure out how to do things in real time without necessarily having the ground right there with us. I think we're capable of that. And we're trying that on the space station. We do a lot of do-it-yourself videos on the space station to prepare for this. And then you can see we have our little tiny dining room table, and that same exit for going outside is where our food would come in, and where we would eventually leave to go back up to the surface. Well, this is the ground crew, and because they were operating on a time delay, they didn't get to talk to us right away. They could talk to us sometimes, but not all the time right away. And most of the time, they just send us messages through text. So, they'd send something off, they'd give a time tag on it, and let us know when they were expecting it done. And they were actually learning a lot. They had also sent down their spacewalk crews to follow along and think about the tools that you would want to build and about the ways that you would want to handle the future. So analogs are important, probably more so for the teams that are planning now versus the crew itself, although I learned a lot from it. So there's our food being delivered and where we slept at night. And here's some of the work we did outside. So this isn't something that you would do at Mars. We wouldn't be attaching arm rails and trying to work off of Mars's surface with that. But it gets you thinking, and they have worked simulations underwater where they've been at the surface of the moon. So they could easily adapt the way out and change it for the surface of Mars. And I'm sure they'll do so soon. And we used jetpacks. That was pretty fun. And so that's the end. That's all the analog. We were there for 12 days, learned an awful lot, and I hope that all of these things will continue on because they're great ways to train everyone at NASA for our Mars adventure.
Thank you. This is wonderful, and I don't think we're that far behind where we're supposed to be. So it's a miracle. Hardly ever happens in the space business. So now it's time for your questions, and we've got these three wonderful folks, and we have Kim on the line also from Hawaii. So please, I'll take a question, and I'll probably repeat the. Oh, is there a mic? Even better.
I have a mic. Yeah, I believe it's on. Ion drive systems are doubling in thrust about every 12 months or so. It's likely that in the next 5 to 10 years, we're going to see them cost competitive for Mars missions against chemical rockets. Do you agree with that?
The thing about electric propulsion, no matter what technology it is that the thrust is driven by the power level that's available. So you really have to be looking, it's not so much an issue with the thrust technology, is it a gridded ion thruster or a Hall thruster or a Vasimir or whatever. The issue is with the power system. So I think right now, today, what is flying commercially, there are over 150 spacecraft flying electric propulsion today. They're mostly communication satellites. Those range in power level between 2 and 20 kilowatts. That's the kind of power level. I showed you the investments that are being made today by NASA primarily in 13 kilowatts for flight, and then there's a very early phase development program for 100 kilowatts, which probably won't fly for probably another 20, 30 years. So in terms of, do I agree that there's a lot of opportunity for higher thrust ion drive systems? Yes. The constraints on that really are in the power system more than in the rocket itself. So I'm not really sure I'm answering your question, but
I was just going to add some context to it. When Roger is, I don't believe I have any volume control.
Yeah.
Just to add some context to it, every time he says kilowatt, think a microwave oven. So when he was talking about 100 kilowatts, line 100 of them up, pop 100 bags of popcorn.
Yeah.
And I don't know, think how much time that would take on the cycle to power all that. So it's an enormous amount of energy to create from whatever source that you're creating. And it's extremely efficient. But it has that
yeah,
overhead.
ion drives are great, but they take a lot of power. I said, I think at the beginning, that the International Space, I'm not sure I said it, but the International Space Station is about 200 kilowatts. And that is by far and away the highest power system out there. So that's...
Spirit and Opportunity, I think, peaked out at like 65 watts.
Right,
So,
and Curiosity has like...
0.065 kilowatts at high
Right.
noon.
And Curiosity has about 100 watts,
Yeah.
something like that. The MMRTG. And Pluto New Horizons is about the same. So we're talking about a lot of power relative to that. So...
Questions? Yes.
I'm not sure who to address this to, but if humans are only going to live in space for 6-9 months before the radiation can get to them, doesn't that pretty much limit? Yes, we can accelerate them a little faster and get them, but that kind of limits the radius of how far humans can go, or are there what's beyond that? How do you get people beyond that?
I think Chris has the answer to that one.
Yeah, it's just bringing the infrastructure along with you that allows you to protect yourself. So, our journeys to the moon and back have been quick trips because of the risk, and you essentially take a dose when you're doing that. So this is something that if we want to have any amount of long duration stay, just like it takes kilowatts of energy to do efficient propulsion, it's going to take tons of mass. You're hollowing out an asteroid or living in a cave. We have to create the space equivalent of that. But keep windows so that we have something to look at.
I have a quick question. We've been talking about the Martian all night, but are there any other science fiction tales that you think really get things right? Like I really like 2312 with the hollowing out of the asteroid, but for Christmas giving, would you suggest any reading? And Kim, if you want to get in on this, you're welcome to as well.
Yeah, I mean, this isn't science fiction, but I always give family and friends Mary Roach's Packing for Mars to learn more about this sort of general area. It's a really good book and really very readable and funny. Actually, I know you said aside from The Martian, but I wanted to just point out a couple of scenes in The Martian that really resonated for me. One is the one where he ran out of ketchup. Never underestimate the importance of condiments in space. And the other is, as I pointed out in my talk, there's this connection between cohesion and the tendency for a team to be more independent, maybe even too independent. And the crew in The Martian was very cohesive. And what did they do? They mutinied. So I thought that was a really nice example of what I was talking about there.
Dottie, did you have any?
Okay. I guess the other thing I would mention, I think those are great suggestions. Well, I don't think this is
Here, try that one.
Okay. The other thing I think more and more, and probably because my other background is history, is I'd actually read some books of folks that have gone out and explored and think about what it takes both as a team and as individuals to leave the people that you have relied upon, the society that you think about a lot, the families, and when you go off, you don't know, and they don't know either, if you're going to come back. And so I think that would be really important too. And there's so many good examples out there, so I don't want to limit it. But I just think having a historical perspective is important too.
I'll add in a local one since the destination was here, but Undaunted Courage. The story of Lewis and Clark is when they're packing up in St. Louis, it's interesting to think about the journey that they're about to go on.
And I was going to say there's a movie coming out, In the Heart of the Sea, which is the real story of Moby Dick. And you wouldn't think that that would be a good thing to read about space, but some of the same issues come up, that these people have to survive for weeks in an isolated environment. So I would say read the movie or buy the book. What? What? Watch the movie, read the book.
I would also, this is on?
Yeah.
Okay, so I would also say that you should think about not just the explorers, but in terms of establishing a sustained human presence beyond Earth, how did this country expand from the 13 colonies out to be a continental, to encompass the entire continent? And what were the ways that the government worked with industry to make that happen? How did the economics, how did they make it affordable? How did they make the economic expansion of our country work? And it's a fascinating story, and it really is a partnership. And so I would encourage you also to think about that. As you think about exploration, think about what happens after you've done the initial missions.
Any questions?
Two questions.
Okay.
Right here.
Mm-hmm. Hi.
Would you like to comment about the economics of a space elevator as a low-cost way to get materials into low Earth orbit? And secondly, if we're going to decommission the space station, the International Space Station, which is pretty costly to keep up, why not just load it up with supplies, put 20 of these 10 kilowatt ion machines and send it off to Mars? Does that solve two problems?
So you had two questions. So I think the way we look at technology and the way NASA looks at technology and the Department of Defense is that you look at different time horizons when you're picking your investment strategy and how am I going to accomplish the next set of things and beyond that. And there are various technologies like space elevators. That's one example of many. Fusion rockets, nuclear electric propulsion, that are really hard to do. There are some fundamental challenges. They're not impossible, probably, but they're not easy. And so you put those you give them some money, you invest some, but you don't put all of your eggs in that basket because you don't know, there's too much risk, right? Alan talked about balancing all of those factors. And so there are a variety of technologies like that us in the community put in that category, including space elevators, for example. If it works, great, right? Put a lot of what I do out of business. That's fine with me, right? But it's not going to happen for a long time. And so in the meantime, if you guys want to go to Mars, right, and establish, the initial permanent sustained human presence on Mars, it's probably not going to be with space elevators. But maybe your kids or your grandkids will use space elevators. So your second question.
International Space Station to Mars. That you're not the first person to suggest that. It's hard to do. This ISS is enormous, and it would take a lot more than 20 10 kilowatt ion drives to get that to work. But who knows? Dottie,
yeah, and the other part I was going to mention about it too is that when it was built and the way it was built, of course, was working for the way that we currently work NASA, which is having a ground crew that can monitor everything and a crew that does not interface with it. So unlike the shuttle where I talked about all those switches and circuit breakers, it's very much not like that. And so the ground does a lot of the work while we're sleeping, and we fix things, we fix the hardware, but we don't have all the interfaces to control it. So that would be a problem. The other problem is that it was built to last a certain amount of time. And although we have seen things that have lasted way beyond the life that we thought that they had. So I would say that this is very good engineering, but the seals that hold the structure together are one of the limiting factors, and they will be coming expired in the time frame that it wouldn't work.
That no one was injured when Spirit stopped working.
Right.
Right. Yeah, we actually built the power system on the ISS. our team did, and we are starting to see some real degradation in the power system along the lines of what Dottie is saying. So sounds cool. And actually there is one step back from that, which is to take a module, a single module or a piece of it, and modify it extensively along the lines of what Dottie is saying. Provide that autonomy that is necessary, and then maybe we could do something.
I have a question for Kim with regard to the high seas missions. Have you tested for the role of art and music in the happiness of the crew in the long-term missions?
I'm not sure if I heard that correctly. You're asking about the effect of art and music on psychology, is that right?
Yes, that's correct.
Okay, great. The short answer is not explicitly. However, we have had some studies that are related. So we had one very small study which was looking at using robotic pets to help the crew stay happy. That was quite interesting because what it seemed to show is that people who grew up with pets loved them. People who did not grow up with pets hated them. So there's that. We do have a planned study for the next mission, which is looking at providing virtual reality is a bit strong, but essentially a virtual window. So a large virtual window which could show the view outside, but it could also show a beach back on Earth. It could show a forest. It could show animations. It could show an abstract image. And so the study is going to be looking at which of those the crew prefers and how they help the crew with their psychology. But yeah, it's something that's very important. And we do know, at least anecdotally, that the crew find listening to music, particularly music they all like, watching movies together, playing games together. All of these things are really important.
Just to follow up on that just for a second, there's actually a group right now that's asking the question, if we could take an artist to the moon and they had 12 hours on the moon with an astronaut to help them, what piece of art would they build there? It's actually a competition. It's called Giant Steps. If you're interested, you can Google it. And the submissions, I can't remember exactly when they're due, but there will be an exhibit of the winning submittals here in Seattle, and it's a worldwide competition. Next, I think it's in May of next year, but you get to look at the website. Anyway, so following up on that, they're trying to ask those questions.
Can I add just one more small thing? Another book recommendation from the earlier question, I would recommend Bold Endeavors by Jack Stooster. So he was looking at Antarctic exploration, submarine exploration, all of those past examples of human exploration, and trying to draw some conclusions about deep space exploration. And one thing to note is that on Shackleton's Antarctic voyages and several others, they would put on plays. They would take pictures. They would brought costumes. They'd cook for each other, even if what they were cooking was another variation on seal blubber. Creativity is very important in maintaining cohesion in a crew. So I think we've got a lot of data to support that. We've got less data to support the importance of art that we bring along with us, but I think that's something we need to explore.
Okay, we've got questions piling up. Go ahead.
Hi, my name is Magali, and I have a question for Chris from Planetary Resources. Can you briefly kind of go over a little bit of your ACS system? What makes it better, or what is different? I did read a little bit about it. I worked on spacecraft, and now I work at Aerojet at propulsion engineering. But I'm very interested to know, do you use any propulsion system? And I saw in the pictures that you're using CubeSats, right? But your next mission seems larger. So I'm just curious.
Yeah, so ACS stands for Attitude Control System. And in space, you don't have anything to push against. So that's why you either have to throw things overboard, like propulsion, or fire extinguishers, depending on your choice of movie references. Or you manage what's called momentum with reaction wheels or momentum wheels, and there are all sorts of ways of doing that. So on the Orchid 6, we have pretty much most everything in the spacecraft we've built entirely in Redmond, 5 miles south of where the rockets in Redmond are made. And we do this because typically with the aerospace approach for doing things, you make things ultra high performance. They're made for particular types of parts. They're space qualified. They go through all these very complex, very rigorous processes to ensure that they'll work when they come out the other end. And what that results in is spending a lot of money for just a few copies of things. But we knew when we wanted to build lots of satellites and go out to asteroids and use swarms of satellites for doing that we would need hundreds and hundreds, maybe thousands of reaction wheels, for example. So we built them ourselves. So in this case, we're looking at ways where we can take, ordinary things that you can buy off catalogs on the internet from industrial supply houses, and how you can make something very precise like one of these wheels work. The other part of it gets to working with the entire system and how you could point a pencil of light through a laser, not at an aircraft. Don't ever do that. But you can point it back at the Earth when you're out at an asteroid, so that you can use fiber optic communication without the fiber, so to speak. You're using the vacuum of space, but because the laser is very, very pinpoint, you have to keep it very stable. So what we look to do is, instead of making the most precise reaction wheel that's ever been made, like something that might be installed on the Hubble Space Telescope, we make something that's pretty good, but we make it work well with another system that then takes out the vibration on the reaction wheel. And for anyone who has flown a drone and has put a camera on it, a lot of times you get those camera mounts that react very quickly, and they take all the vibration and the jitter out of what's going on with the drone, but the drone still can roughly point it. So that's the type of things that we're looking at. Instead of solving the whole problem all in one place, we're looking at the way that we can break the problem up into different areas and focus on that local solution. So that's one example in the area of attitude control of what we're doing. We'll add propulsion into it in the future. But
Okay, so we have about 12 minutes left. We'll go with the gentleman in the blue plaid shirt, and then the young gentleman over there, and then the lady with the red hair. So.
So this is a question for Dr. Myers. So you mentioned in your talk that the scientists that are concerned with the health of astronauts are concerned with astronauts' flight times longer than 6 months, and part of that would be the fact they're going to be in zero gravity for the majority of that time. But there have been some talks about using make spin gravity, like you saw in the Hermes and the Martian. So I was wondering if any of the current trades that are being done are including some sort of centrifuge or some artificial gravity generation for the astronauts.
To my knowledge, what they're doing is they're not trying to spin the whole spacecraft right now, but they are looking at putting on board the small centrifuge that is flying on ISS, for example, and things like that. But the problem with that is it's really heavy, and so they're looking at ways to try to get it lighter. So that, again, trip time is all about thrust to weight ratio, right? And so if you put more equipment on, it takes you longer to get there. And so they are not actively, there are lots of concepts for, cables between two modules and trying to do it inexpensively. But again, balancing risk and money, right now, most of the work that I've heard of is actually putting a smaller centrifuge on board, or just doing a lot of training without anything artificial, no artificial gravity of any kind, but
they had looked at making very small exercise equipment that you could use to do the countermeasures that we, now the equipment used on the International Space Station is large. It's and pulling against vacuum cylinders, and that wouldn't work. But we use smaller ergometers in the shuttle, but even they were pretty big. So they've been trying to look at smaller exercise equipment as well.
I should say one more thing, which is that none of these simulations of gravity are perfect. There is degradation, almost, to my knowledge, no matter what.
Yeah, in fact, some studies that they have done have shown that even though you're constantly working on space station and you dedicate all this time to working out, that people are still coming back with some of the early symptoms. They do not ever become diabetic, but it's like the onset that you would have that same kind of rest scenario where you're not really working.
Okay.
Hey. Okay. My name's Harrison Jerome. I have a question about colony on Mars. So it seems like one of the biggest problems with getting to Mars and staying there is that there's a big problem with radiation. And you went into some detail about the problems on the way to Mars, the 6-month trip, and there are ways to shield them from the radiation. Is there a different way that they could possibly do that on Mars that could utilize soil, or would it be sort of the same process as on the way to on the transportation?
I think Kim actually talked about the lava tubes. Kim, you want to weigh in on this?
Sure, although I'm not a radiation expert, so please take it all with a grain of salt. Essentially, what you want is a lot of material. So the reason it's more challenging when you're in space is it's hard to have a lot of material in space. Once you're on the planet, you can look at solutions like piling up giant piles of rocks or going into lava tubes. Or one proposal I saw involved crews storing, and this sounds gross, but it's a nice idea, storing their own waste in the walls of the habitat, because water is quite a good radiation protection, and so they can have the walls be part of the protection. Yeah, but then doing that in transit is harder. So I just wanted to point out that there's one other possible solution that I didn't hear anyone mention. And again, I have to say I'm not an expert, but the idea of radiation hardening the humans as a possibility. So what could you do in terms of, could you provide medication which allowed humans to be more radiation resistant? Could you, I don't know, do some genetic engineering or something crazy sci-fi like that? So I think that we need to consider pretty much all the options for radiation. Of course, the one that was discussed and is the most obvious is getting people there faster.
I think another thing that people have talked about is electromagnetic force fields, some sort of active radiation.
A large magnetic field using a big super. Yeah, that sounds great, but when you do the math, it's really hard to do that, to get a big enough magnetic field that's strong enough.
Yeah, all these are reasons why you should be thankful the Earth has a dynamo and we have a magnetic sphere.
Yes.
The magnetospheres.
Amen to that.
This woman has been waiting for a long time.
It was on.
There it is.
Well, thank you. This was really informative and kind of amazing and has awoken my imagination. I had 2 questions, but since we're short on time, I'll go to my second alone, which is for Dottie. Where did you get that cool T-shirt?
Oh, so the T-shirt is a great lead-in because we have so many young people in the audience as well. So tonight is a perfect opportunity. We are talking, we're engaging in dialogue about the future in Mars, and there's a new nonprofit out there, the MarsGeneration.org. And its goal is to get people talking and to send young people to space camp that can't afford it, and to create ambassadors that are young people. So all of you guys could have the potential of being ambassadors within your own communities and going out and talking about what you've learned and what you want to learn about space. So the MarsGeneration.org, and I'm part of the launch support team.
Is it okay if I mention one other opportunity?
Yeah.
So we're on the 12-month mission at High Seas right now. We are going to be doing 2 or 3 8-month missions over the next few years. We're going to start recruiting for those early in 2016. So come join us on Mars.
We might have time for one more question, if anyone has a question. This gentleman in the front row. Just a second, we'll get the microphone to you.
Sorry.
Oh, there we go.
Nice try.
So I had a question about since there was a
space race to the moon during like the Soviets and Americans during the Cold War. Do you think there would be a race to Mars once the funding and technology comes around between like privately funded companies, NASA, like SpaceX, things like that?
You mean between international?
Yeah.
I actually doubt it. I hope not. I hope we're cooperative instead of competitive. You never know what the future holds, so nobody can say no with any certainty, but I hope not. There's too much to be gained from cooperation. With the International Space Station, it's an incredible example of a huge international project. Many feel, and there are lots of data that suggest it's the largest human endeavor ever done as a species. Mars will be that on steroids.
Some people talk about if China advances with its space program, there's a scenario where you might have a space race with China. China says, hey, we're going to send people to Mars, and so we got to beat the Chinese to it. But B is China says, we really want to do something with you. We've got a lot of money that we can spend on this. We don't have the expertise. Let's go together. Do you think people would go for that sort of thing?
I sure hope so. But you're absolutely right. Those are the two scenarios that are probably the most credible in terms of extremes today. And I hope it's the cooperative way. We'll go a lot sooner, probably because it's really hard, and we'll be more successful, and we'll go to stay instead of like Apollo, where we won the space race, but we haven't been back. I want to go to Mars to stay.
Amen to that. So we'll turn it back to Richard for some closing comments.
Well, I want to thank everyone for coming. I think it was a great program tonight. I want to thank all the speakers again. I think they were fantastic. And thanks to Kim for being with us remotely. Maybe that's a little bit like what being on Mars will be like, except not much delay. So anyway, our next program is in January. It'll be the future of the human body. So watch our website for that. More information about that will be upcoming.
What is that website?
It's mitwa.org.
So I want to hear a speaker at that one that talks about Kim's idea about genetic and engineering of humans to be more radiation tolerant for Mars.
Well,
excellent.
He's actually leading that program, so he knows.
Good. Thank you.